संजय संजय देखो कि हम आ गया गया था वो ऑटो तो दूसरे साइड था रोड पे खड़ा था खड़ा था तो वही एक ऑटो में जाता था नहीं छोटा देख लिए हाँ।
Currently serving as associate dean for grants consultancy, and industrial research. He plays a pivotal role in promoting sponsored research and industry collaborations at the Institute. He joined BITS Pilani in 2005 after submitting his PhD thesis at RRI, where he earned his doctorate in physical science under the affiliation of JNU, New Delhi. Professor Gupta's academic journey began at University of Calcutta, where he completed his MSc and PhD degrees in physics. His core research expertise lies in condensed matter physics, particularly focusing on ultra-thin films, nanomaterials, and their applications in devices and sensors. In terms of research output, Professor Gupta has authored over 160 peer-reviewed publications, contributed several book chapters, and produced more than 5 PhD scholars have formally graduated under his guidance. His research has garnered more than 3,600 citations with 8 index publications, reflecting the impact and complexity of further academic collaboration and global exposure. So we offer a warm welcome to Professor Gupta, and now Professor Gupta will take over as the external examiner for the PhD of Mukesh Chandra. So over to Professor Gupta.
Thank you, ma'am, and good morning to all of you. Uh, I think there were some issues with the audio. I could not able to hear many of the things, but yeah. So if there is any format of this, kindly share that format, like how the things will go, whether the candidate is allowed to make the presentation or complete the presentation and ask the questions afterward, or in between one can ask. So, what is the format of the defense? Can anyone tell me?
हाइट पे क्लिक कीजिए.
Sir, uh, can you start the process of presentation by Mukesh Chandra Bose, if you allow us?
Yeah, you can start the thing. I just wanted to know, is there any format for the Viva Bose defense? Is there any format like
Yes, sir. We have one form that is recommendation form and other related documents. So that with you presentation.
okay, okay, then
Hello.
yeah, you can start the presentation.
Thank you, sir.
Good morning, sir, and all the respected faculty member and PhD students. Myself, Mukesh Chandra Bose, and my supervisor is Dr. Santosh Prasad Gupta, Assistant Professor, Department of Physics, Patna University, Patna. The title of my PhD research work is Investigations on Neoteric Phase Behavior of Amphiphile Water Systems mediated via strongly binding counter ions. My thesis contains 7 chapters. The first is the introduction, in which I have introduces about the different phases present in the aqueous media of the amphiphiles. The second is the characterization technique, in which deals with the different phases present in the aqueous media of the amphiphils. Chapter 3 is the general phase behavior of surfactant systems. Study. 4 is the relative stability of the column and columnar square phases of discotic molecules, a theoretical study. Chapter 5 deals with the phase behavior of aqueous solution of sodium dodecyl sulfate in the presence of para-toluidine hydrochloride. Chapter 6 introduces about the different phase behavior of an aqueous solution comprising of anionic and cationic surfactant mixtures. Chapter 7 is the summary and future aspects. There are 3 articles in the Scopus Journal of Molecular Liquids. The first article is a theoretical investigations on relative stability of the columnar, hexagonal and columnar square phases of discotic molecules. The second article is effect of para-toluidine hydrochloride on the phase behavior of aqueous solution of sodium dodecyl sulfate. And the third article is investigation on phase behavior of an aqueous solution comprising anionic and cationic surfactant mixture. There is also 2 book chapter written in the name of the book is Advancement in Contemporary Physical Sciences. The first files and their self assemblies, whereas the second book chapter is experimental techniques for the characterization of the lytropic liquid crystal phases. In chapter 1, this is the amphiphilic molecule, which has 2 parts. First is the hydrophilic head group and the second is the hydrophobic tail group. The head group can be anionic, deuterionic or uncharged, whereas tail group is made up of hydrocarbon. Lipids and surfactants are amphiphils. Surfactants are artificial, whereas lipids have biological origin. Some examples of amphiphils are the first 2, that is the sodium dodecyl sulfate, and AOT is anionic surfactant, whereas CTAB is cationic surfactant. Here PC is the deuterionic surfactant and polyethylene ether is the non-anionic surfactant. Initially, when amphiphilic molecules are added to water in aqueous media, initially they disperse and some will migrate to the surface to reduce the unfavorable contact between hydrocarbon tail and water. The molecule exists monomer. Concentration called the critical micellar concentration, that is CMC, aggregate starts form in the such a way that the hydrophilic head and hydrophobic tail becomes shielded in the aqueous solution environment. They are capable of forming shapes like a sphere, cylindrical micelle and bi-micelle. The shape of the micelle depends on the packing parameter. When the packing parameter is less than 1/3, then its shape is cone and it is capable of forming the spherical micelle. But when the value of CPP, that is the packing lies between 1/3 to half, then its shape is like truncated cone and forms cylindrical micelle. Its value is equal to 1, its shape is like a cylinder and forms bilayer. Further, if value is greater than 1, it is capable of forming the inverted micelle. When we increase the concentration of amphiphils in the aqueous media, initially we get the monomer phase. Then on increasing just above the CMC, that is the critical micellar concentration, we get the spherical micelle. A spherical micelle forms the body-centered cubic phases. Further increasing, the spherical micelle is fused into the cylindrical micelle. and cylindrical micelle is capable forming of hexagonal phases. Further increasing, the cylindrical phase is fused into bilayer, and bilayer is capable of forming the laminar phases. Further increasing, we get the inverted micelle. In chapter 2, we have introduces about the different techniques to determine the existence of different phases in the aqueous media. The first is the small angle X-ray scattering. This has been shown the experimental setup of the X-ray scattering. This is the source of X-ray from where X-ray is generated. M is the monochromator which allows the X-ray 1.54 angstrom. C is the collimator, and S is our sample through which coming X-ray is scattered, and we get a diffraction pattern. The figure is showing the diffraction pattern. Using this technique, we have got the diffraction pattern, the amphiphile Bartas system in the presence of various strongly winding counter ions. Analyzing this pattern, be able to identify the various phases, and also we have reconstructed the electron density map for the important phases. Second is the polarizing optical microscopy, which is widely used to identify the different liquid phases. Liquid crystalline phases are birefringent and show characteristic texture between cross polarizer under optical microscope, which arise due to the defects present in the medium. This defect creates deformation in the medium over length scale of the order of tens of the micrometers due to the low elastic constants of the. Since the type of the defects in the medium is determined by the symmetry of the structure, the texture resulting from these defects are characteristics of the phase. Therefore, this texture can be used as fingerprint to identify the different liquid crystalline phases. Here, the texture is showing the fan-like structure, which is showing the existence of hexagonal phases. In chapter 3, we have used Ginzburg-Landau theory, which is a single scalar order parameter for a study of mixture involving surfactant and water systems. Here, in the figure, we can say that this is the amphiphilic molecule. When we added in the aqueous media and increasing the concentration, initially we get the spherical micelle, which forms the body center cubic phase. Further, increasing this spherical micelle is fused into cylinder and which forms hexagonal phase. Further, increasing the cylindrical micelle is fused into the bilayer micelle and forms laminar phases. Further increasing, we get the hexagonal phases of the inverted micelle, and again further increasing, we get the body center cubic phase of inverted micelle. All these order phases like a body center cubic, hexagonal, laminar, and so on, considered as the distribution of water, matter matrix, and vice versa. This problem is the mixture of two liquid systems and can be characterized by a single order parameter, that is the concentration of amphiphile, and the average free energy density F is given as. Now, in this equation, F is the free energy density which has obtained by the integration of local free energy density and divided by the whole volume. In this equation, we have used the Ginzburg-Landau theory up to the fourth power of the scalar order parameter. F of psi r is the local free energy density of the homogeneous scalar order parameter. Psi r and A and B are the parameters. Now, a scalar order parameter can be written as the sum of two terms. First is the psi naught, which is a constant, and second is the modulated term. Here, psi is the Fourier amplitude. Here we have used only the first cell of the reciprocal lattice vector, and hence only those reciprocal vectors which belong to the first cell. Now, we have obtained the different phases. A is showing the lambda phases of the bilayer. Here AL is the lattice parameter, whereas B is showing the reciprocal lattice vector. In figure C, it is showing the hexagonal phases, and D is showing the hexagonal phases of the reciprocal lattice. And figure E is showing the body-centered cubic phases of direct lattice, whereas F is showing the FCC reciprocal of the BCC, and it is now the latter phases can be considered as the convolution of bilayer with one-dimensional lattice, whereas hexagonal can be considered as the convolution of cylindrical micelle with two-dimensional hexagonal lattice. And the body-centered cubic phases can be considered as the convolution of a spherical micelle with three-dimensional body-centered lattice. Order parameter and free energy. Here, a scalar order parameter for disorder phases, laminar phases, hexagonal phases, and body-centered phases, and corresponding free energy density for disorder, laminar, hexagonal, and body-centered has been derived here as these are the scalar order parameter for the disorder phases, for the laminar phases. Here we can see that the a scalar order parameter for the disorder phases can be written as a single term, that is psi naught, but for the laminar phases it can be written as the two term. First is the constant and second is the modulated term, where SL is the Fourier amplitude. For hexagonal phases it can be written as the sum of two terms. First is the constant and other are the modulated term, where SS is the Fourier amplitude. For body-centered cubic lattices, psi b is the scalar order parameter for the body-centered phases, and this has been written as the sum, where first is the constant and other are the modulated, where SB is the Fourier amplitude. Using this term in previous equation for determining the free energy density, we get a different energy value for the disorder phases, laminar phases, hexagonal phases, and body-centered cubic phases. In equation, we are seeing that the energy density is a function of three terms. First is the A, second is the B, and third is the scalar order parameter psi naught. Now, for different values of A, B, and psi naught, we get different value of free energy density, and plotting them, we see that in figure A, it has been plotted average free energy density versus average concentration psi naught at constant value of B is equal to 0.1, whereas value of A has been taken for three terms, that is first for A is equal to minus 15, second is A is equal to minus 9, and third is A is equal to minus 3. For the particular value of A is equal to minus 15 and B is equal to 0.1, and for different values of concentration psi naught, we get that different values of average free energy density, and plotting them, we get the different plot. Here we can say in the figure that as the average concentration is increasing, initially we get the green line which is showing the disorder phases. Further increasing, we get the blue line which is showing the body centered cubic phases. Further increasing, we get the red line which is showing the hexagonal phases, and further increasing, we get the black line which is showing the lamellar phases. Further increasing, we get the red line which is showing the hexagonal phases of the inverted micelle, and increasing the concentration, average concentration, we get the blue line which is showing the body center cubic phases of inverted micelle, and further we get the disorder phases. Similarly, this has been derived from putting the value A is equal to -9 and B is equal to 0.1, we get again the different phases. And further we put the value of A is equal to -3 and B is equal to 0.1, we get the different phases. But as the value of A is increasing from -3 to -15 to -3, then we are seeing that the all four phases are coinciding. In the figure B, we have plotted the free energy density versus average concentration, keeping A as constant and equal to -15, and we have put three values of B here. B is equal to 0.1, B is equal to 0.5, and B is equal to 5. And in further increasing the concentration, we can say all the four phases present here, and as the value of AB is increasing, all the phases are coinciding. Now this has been plotted parameter A versus average concentration psi node at B is equal to 0.1. As the average concentration is increasing, we get the different phases. Initially we get the disorder, then BCC, then Hessian, then we get the lamellar, further we get the hexagonal of inverted micelle, then we get the body centered cubic phases of inverted micelle, and then we get the disorder phases. This graph is showing the parameter B versus the average concentration psi node as constant A is equal to -15. Here we are seeing that as the concentration is increasing, we get same order, but this figure is showing the nature of curve as the hyperbolic, whereas the above figure is showing the nature of the curve to be parabolic. Now we have plotted the different contour plot of electron density map. Here we can see that this is the contour plot of body centered cubic phases. Initially just above the CMC, further increasing we get the hexagonal phases of direct micelle, further increasing we get the lamellar phases, and again increasing the concentration we get the hexagonal phases of the inverted micelle, and further increasing we get the body centered cubic phases of the inverted micelle. In chapter 4, our focus is to study the relative stability of the columnar square and columnar hexagonal phase of discotic molecules using simple Ginzburg-Landau theory. Here, the discotic molecules is consisting of a rigid core and flexible alkyl chain. The scalar order parameter phi r can be written as the local volume fraction difference between the rigid core and the external alkyl chain region of the discotic molecules. As the concentration is increasing, we get the different phases. Initially we get the columnar hexagonal, then we get the columnar rectangular, then we go to the columnar oblique, further we get the columnar tetragonal, columnar lamellar, columnar helical, columnar plastic, cubic phases. Now the free energy density F can be written as the F is equal to integration of F of phi r, which is the local free energy, and using the Ginzburg-Landau theory up to the fourth power of the scalar order parameter, we get the different phases, and they have been plotted here. This is showing the hexagonal phases of the direct micelle, whereas this is showing the square phases, and further we are getting the hexagonal phases of the inverted micelle. Phase behavior. Parameter, we have plotted the parameter A versus the average volume fraction difference at the constant B is equal to 1. As the concentration is in volume fraction difference is increasing, we are getting the different phases, and this graph is showing the parameter A versus the average volume fraction difference. By note, here we have kept B is equal to 5, and again we get the different phases. In this figure, we can see that as the B is increasing, our graph is expanding. Now, the order phases, notably a square and 2D hexagonal phase, are stabilized by the current theoretical analysis. Moreover, the direct hexagonal and reverse hexagonal phases are identified in the curve, with the phases occurring in the following sequence: disorder phases, hexagonal phases, square phases, hexagonal phases of inverse micelle, and then we get the disorder phases. Contrarily, the H1 and H2 phases for each we take up to the 45% of overall area of the order phase, while the stability area of the square phase is approximately 10% of the entire area of the order phases. In chapter 5, we have discussed about the behavior of para-toluidine hydrochloride with the surfactant sodium dodecyl sulfate. The figure is showing that this is the showing the sodium dodecyl sulfate, which is anionic surfactant, and this is the para-toluidine hydrochloride, which is a hydrotrope. Actually, hydrotropes is a molecule which has also two parts. One is hydrophilic head group and second is hydrophobic tail group, but they are not able to forming self-assemble or micelle, but it helps to tune the micellar surface in decreasing. Such molecule, often called the hydrotropes, decrease the spontaneous curvature of the micellar surface, leading to the formation of long worm-like micelle in many applications, amphiphils. Now, keeping the molar ratio, that is the molar ratio of the PTSC to SDS for the constant bed fraction at 50 degrees centigrade, and we vary the molar ratio from 0.0 to 1.4, and we kept upper sample in an incubator for a week, and then on examine by the small angular X-ray diffraction and the POM, we get the different phases. Initially, we get the hexagonal phases, then we get the lamellar phases, then we get the lamellar phases with isotropic phases, and further we get the isotropic phase. Now, the diffraction pattern is showing that the de-spacing between the two peak, that is 100 and 110, each 1:1√3, which is confirming the existence of hexagonal phases. Also, the smooth structure under the cross polarizer also confirming the hexagonal phases. This is the smooth texture, and this is the electron density map of the hexagonal phases, and this is the model of the hexagonal phases. Now, the de-spacing ratio of the two peak from diffraction pattern, the first is 100 and the second is 200. We get that the de-spacing ratio is 1:2, that is confirming the existence of bilayer. Also, multi-cross and oily stick texture under the cross polarizer also confirm the existence of bilayer. This is the electron density map of the bilayer, and this is the model of the bilayer. Now, we in the diffraction pattern, we are getting the broad peak and optically isotropic texture under the cross polarizer. In conclusion, the impact of PTSC on organic salt on the phase behavior of the SDS and an anionic surfactant has been meticulously investigated through the application of POM and a small angle X-ray scattering technique. We have conducted an analysis of the SDS PTSC water system operating at temperature 50 degrees centigrade and bed fraction 50, and for the various value of alpha, we find that as the concentration of PTSC increases, the system shows distinct phases corresponding to the hexagonal, lamellar phases and isotropic phases with surplus water. In chapter 6, we have introductions about the phase behavior of the cetyl pyridinium chloride and the sodium dodecyl sulfate. This figure is showing the cetyl pyridinium chloride molecule, which is a cationic molecule, whereas this is showing the sodium dodecyl sulfate molecule, which is an anionic molecule. As we prepare different sample, increasing the molar ratio, here molar ratio has been considered as the number of mole of sodium dodecyl sulfate divided by the number of cetyl pyridinium chloride and keeping the bed fraction equal to 50. Now, for different value of molar ratio and using the small angle X-ray scattering pattern and the POM, we get the different phases. Initially, we get the hexagonal phases, then we get the nematic phase of this shaped micelle, then we get the lamellar disorder phases, further we get the disorder phases, and on increasing we get the lamellar phases with excess water. Now, this is the cetyl pyridinium chloride molecule and the SDS molecule, and as their molar ratio is increasing, initially we get the hexagonal phases, then we are getting the nematic phase of this shaped micelle, further increasing we get the random S phases, and then we are getting the lamellar phases. Now, the polarizing optical microscopy and getting the different texture, we are able to identify the different phases exist in the aqueous solution. This texture is showing the smooth and showing the existence of hexagonal phases. Further, as the concentration is increasing, we get the texture, and this texture is showing the existence of nematic phase. Further, this texture showing the existence of random S phases. This texture is also showing the existence of random S phases, while this texture is showing the existence of lamellar phases. This is also showing the existence of lamellar phases. This is also showing the existence of lamellar phases. This is also the lamellar phases. Further, on the diffraction basis of the diffraction pattern, here we can say that the diffraction pattern given in figure A and B are showing existence of hexagonal phases, but the diffraction pattern in the figure C, that has a broad peak and showing the existence of nematic phase. In the figure D and E, we are getting the broad peak, which is showing the existence of random S phases, and F, which is the DS spacing of the two peak is 1:2, that is showing the existence of lamellar phases. All these four diffracted pattern is showing the existence of lamellar phases. In conclusion, the influence of sodium dodecyl sulfate SDS anionic surfactant on the phase behavior of cetyl pyridinium chloride, a cationic surfactant, has been rigorously examined utilizing the polarized optical microscopy and a small angle X-ray scattering technique. We analyzed that the CPC and SDS water system at temperature 50 degrees centigrade and a surfactant volume fraction equal to 50 while valuing the different molar ratio of SDS to CPC. Our finding indicates that with the increasing the sodium dodecyl sulfate concentration, a system manifests consist phases identified as the hexagonal phases, mimetic phases of disc-shaped micelle. Then we get the randomness phases, and then we get the lamellar phases. This chapter, the SDS-PTSC water system displays a novel isotropic phase of bilayer noted for the millimeter average inter-bilayer distances and the short-range positional correlation is at increased concentration of the PTSC as outlined in chapter 5. It would be intriguing to investigate whether the isotropic phase of bilayer can be explained by the broadening the current model of the sponge phase to the attraction-dominated regime. The multi-lamellar vesicle identified in this study may serve as the more effective vector for the drug delivery systems. However, additional research is necessary to investigate their medicinal applications. The isotropic phase may be prolonged to synthesize the isotropic phase. Nanoparticles, the isotropic phase of the particles can be subsequently be utilized in the cancer treatment. Now, this is the bibliography. This is the conference attended by me, and I presented there a poster organized by the Indian Science Congress at Nagpur University, Nagpur. This is the workshop attended by me, Central University of South Bihar, Gaya. This is the X-ray lab at Aizer Mohali. Now I would like to give my heartiest thanks to my supervisor, Dr. Santosh Prasad Gupta. I would like to give my thanks to collaborator, Dr. Santanu Kumar Pal, Aizer Mohali. Collaborator, Dr. Salu Dhingra, Aizer Mohali. Dr. Sanjay Kumar, Head Department of Physics, Patna University. Dr. Smita, Principal BN College. Dr. Raj Kishore Prasad, और faculty Department of Physics, Patna University, all faculty members, BN College, all my colleagues. I would like to give my thanks to members of Department of Physics, Patna University, staff partners of Physics, BN College, staff members of Examination Department, Patna University, lab mate Priyanka Sharma. I would like to give thanks lab facility, soft condensed matter, Department of Physics, Patna University. Thanks to Patna University support and thanks to lab facility Aizer Mohali. Yes.
How to go about Dr. Santosh? Can you? Is it open for the questions?
Sir. Yes, sir. It is open for the question session.
So,
I'll just
if
tell him to be ready for the question.
No. Shall we allow the audience to?
Yes, sir.
Go?
Yes, first, I'll tell the audience to.
So let the audience ask the question and then I can ask.
इनकी आवाज सुनने को लगा इसमें लगाने आ रही आवाज सर अभी तो नहीं आ रहा भाई इससे आवाज नहीं आ रही तो इसको लगा दिया नहीं आ रहा
Let the audience ask the question and maybe after that Is that fine or?
Hello. Sir, there's no question from the audience, so we proceed to that question, sir.
Okay, no issue. So then I can ask a couple of questions, of course, the fundamental level and those kind of questions. So first of all, I'd like to congratulate Mukesh. He himself proclaimed to be completely East. That's what I read from. I think you have some of you have logged in from two devices. I think that is why it is going. Mukesh, am I audible to you? You're not. I think you're mute.
Sir, kindly repeat, sir.
Now, can you hear me, Mukesh?
जी
आवाज आ रही है, मुकेश?
हाँ अब आ रही है सर.
हाँ. So मैं बधाई देना चाहता हूँ तुम्हें
थैंक यू सर.
for the wonderful presentation, and you yourself have declared Dr. Mukesh. No, just I appreciate your spirit for that. So you are a deserving candidate, no issue in that. You have done a balanced work, both theoretical and experimental. You have shown your skill in both the directions, theory as well as the experiment.
Actually, sir, your sound is not clear.
हिंदी में बोलूँ मैं?
जी सर.
नहीं, मैं ये बोल रहा हूँ कि आपका काम दोनों तरीके से है।
सर एक
नहीं आ रही आवाज?
सर क्लियर आवाज नहीं आ रही है.
कैसे मैं टाइप करूँ क्या फिर?
सर
तो
काइंडली रिपीट सर, काइंडली रिपीट.
संतोष इधर व्हाट्सएप पे कॉल करे क्या?
आवाज क्लियर नहीं.
Yes, sir. मैं कॉल करता हूँ सर.
ये मुकेश को म्यूट कर देना, मुकेश को म्यूट करो.
Okay, sir. I'll call you, sir.
हाँ.
Okay, sir. आप म्यूट कर दीजिए.
बालक छोटा से बड़ा होता है तो उसके अंदर जो सेल होते हैं कोशिका